Hi guys, this is Mrs. Bracy with your lesson on radians, arc length, and sectors. And we're going to go ahead and start with your flashcard just to talk about radian measure. You've heard me talk about this a little bit here and there throughout the year. And radian is a way to measure an angle based on the radius and the circumference of the circle instead of in degrees like we normally do. Okay, so a radian is a measure of an angle based on its radius. And in terms of that, and I'll explain why in a moment here, radians are always measured in terms of pi. Okay, so pi is going to represent 180 degrees, and 2 pi is going to represent 360 degrees. And the reason for that, and I have the bottom half of your flashcard covered up here because I don't want you to see that yet, so I'm just going to use my paper to illustrate this for you, and you can write this down or not, you don't have to. So if I have a circle, which I probably could have drawn better than that, and I'm going to say that it has a radius of 1, I want to now represent the circumference of the circle. And hopefully you all know that the circumference is equal to, you can say 2 pi r, or you can say pi d, either way. 2 pi r is more commonly used. And so if we were to plug in a radius of 1, then the circumference of the circle is 2 times pi times 1, or just 2 pi. Now, if you think about the circumference of a circle, but in terms of the arcs that create the circle, which, we could break it up into arcs if we wanted to all along the circle. And as you know by now, that those arcs are going to total 360 degrees. So the entire circumference of the circle is going to be 2 pi. This is, again, when we have a radius of 1. And so that's why we say 2 pi is 360 degrees, because 2 pi represents the circumference of this circle, and it also is 360 degrees, okay? So the radians are 2 pi, and the degrees are 360, and those are equivalent. Okay, now that's imperative to converting between radians and degrees. And so if I want to convert radians to degrees or degrees to radians, you'll see different representations of this, but in my opinion, the easiest way is to stick with a single proportion. Instead of having one way to convert one and one way to convert another, the single proportion can convert both ways, okay? So any degree measure over 360 will equal the equivalent radian measure over 2 pi. Okay, so as you know, 2 pi is 360 degrees, so we have those lined up. And so if I gave you a degree measure, you could plug that in and cross multiply to answer the radians in terms of pi. Or if I gave you a radian measure, you could plug that in and cross multiply to find the degrees. Okay, so, as I said, there are other ways to represent this, but for now we're just going to stick with this as our conversion. The only thing you're going to really have to worry about with radians is converting from degrees to radians. Okay, so that's a way to measure the angles and the arcs of a circle. Other than degrees, we can use radians. Okay, so we'll see that a little bit while we talk about our other two topics today, which are arc length and sectors. Okay, so I'm going to go to the packet, and we're going to go to page 37, and we're going to take a quick look on page 37 at arc lengths and radii. And I'm going to try to go through this page pretty quickly because I think you'll understand by the end that this is all about ratios. Okay, so we're going to take a look at the diagram. We have two concentric circles. That just means one is inside of the other and they have the same center. And when circles are concentric, it can be shown that the two circles are similar by using a transformation of, as you know, a dilation. So we now know that our circles are in fact similar. We're going to represent the ratio of similitude of the smaller triangle to the larger triangle. So the smaller circle and the larger circle, we can only do this with a radii because that's really the only thing we know about them. The smaller circle has a radius of r1, and the larger circle has a radius of r2. So the ratio of their similitude is r1 to r2. Okay, so the same dilation, which maps what we're looking at now are slices of the circle. So the same dilation would map the smaller slice into the larger slice, which we call sectors. That's the vocabulary word here for them. Okay, and such a mapping of the slices will only occur when this angle measures the same. Okay, so will only occur when theta is the same for both. okay? Or in other words, the central angles are congruent. Those are central angles, okay? And such a mapping tells us that these slices or sectors are in fact similar, just like the triangles are similar. Okay, so we're just going to look very quickly through these next two proportions. So if I have R1 over R2, that's going to equal S1 over S2. Notice S1 is the length of the arc created for the smaller triangle. S2 is the length of the larger arc created by the larger circle. So the ratio of the radii is equal to the ratio of the slices or the arcs that were created. Okay, we can also say that, as you guys know with similar, you can say R1 to R2, or you can say S1 to R1 and S2 to R2. Okay, and that's just because we can kind of rearrange those proportions. Okay, so what we end up having here, if we want to take a quick look at number 7, is that we simply are looking at the ratio of the arc length intercepted by a central angle to the radius of the circle, okay, will always yield a constant ratio. And so that part is just important to understand when we take a look at our conclusion, that the length of the arc intercepted by a central angle is proportional to the radius, okay? So we called them R and S in the example above. And so what this allows us to do is to find the length of that arc given certain information. Okay, so we can do this in terms of degrees or in terms of radians, okay? And as you know, 360 is 2 pi, so that's the only difference in these two equations. And here are the equations for your arc length of a circle, okay? S is the arc length, or that sector, that section of the sector, okay? Pi over 360 is the proportion of the circle. Think about a circle being 360 degrees. Theta is that central angle. So we're just saying what portion of the circle that sector is taking up. So if it's a 60-degree angle, it's 60 out of 360 of the circle. You just multiply that by 2 pi r, which is the circumference of the circle, and you will have that length. This works as well for radians, where theta over 2 pi would represent the radians. This can actually be simplified, as you see here, because it has 2 pi here and 2 pi in the circumference. Those can actually be canceled out, and so in terms of radians, S can be theta times the radius, okay? You know, that I don't really worry about, because I can always set it up like this and end up canceling later, and because these two are so similar, I just like to kind of think of this, and you're going to see that in a moment on your flashcard. Let's take a quick look at an example. Flip the page here to 38, and let's take a look. We're going to do number 2 because it's a little bit simpler, and then we can look at some more complicated examples in class. So for number 2, a horse on a lunge line travels in a circle around its trainer. The radius of the horse's circle is 24 feet, so I'm going to represent the radius as 24. The angle between location S and P on the circle is 140 degrees counterclockwise. So from S to P counterclockwise, I'm going to draw in the other radius here. This angle is 140 degrees. Notice we're in degrees. Find the length the horse travels from S to P in feet to the nearest foot. So I'm going to call it S for arc length, and to find that, we're going to do, since we're in degrees, S equals, and we're going to go back to the formula from the previous page, which was theta over 360 times 2 pi r. And so in this case, S is going to equal the central angle, which is 140, over 360 times 2 times pi times the radius, which was 24. And so if you have a calculator, you can use that to solve this, but I'm just going to tell you that it turns out to be 59 feet. Okay, so we have an answer of 59 feet. And that's how you find arc length. Okay, we're going to move on to area of a sector, so go ahead and turn to page 39, the next page. And the area of a sector, I'm actually going to rush through this page really quickly because a lot of this is just kind of common sense. The area of a circle is pi r squared. Okay, and so for half a circle, it's 1/2 pi r squared. Quarter circle is 1/4 pi r squared, and so on for any ratio that you have. Okay, what we have is half of the circle comes from the fact that if you just look at this example here, there's 180 degrees in half a circle. And so the ratio is actually 180 over 360. Okay, and so the area of the sector, which is, this is the ratio, the area of the sector to the area of the circle, which is pi r squared, is going to equal 180 over 360, which that reduces to 1/2. So that's why the area is multiplied by 1/2. So if I just multiply this to the other side, I have 180 over 360 times pi r squared, which is the same thing as this 1/2 pi r squared, but that's because the ratio is 180 to 360. Okay, so any angle that you have, you can replace that into that 180. So anytime you want to find the area of the sector of a circle, you're going to go ahead and do theta over 360, just like we did for arc length. But this time you're going to multiply it by pi r squared, okay? Theta over 360 times pi r squared. Okay, so that will work very similarly for radians. Okay, and so if it's in radians, you're going to say theta over 2 pi times pi r squared. Okay, so we just replaced the 360 with the 2 pi. If you wanted to, you could cancel out the pi's, but again, I just kind of keep these the same and then just work from there, simplify from there. All right, one quick example. Let's take a look at number 1 on the next page. We have the area of a sector shown at the right. We're going to find the area of the sector. The radius is 5 units, which is labeled, and the length of the minor arc is 3.93. So if we want to find the area of the sector, we need, this is going to be theta over 360 if we're in degrees, times pi r squared. We know the radius, but we don't know the central angle. So we're going to have to go ahead and find the central angle by using the fact that we know the sector length. So back to our sector formula, theta over 360 times 2 pi r. Okay, now we know that the sector is 3.93, and that's theta over 360 times 2 times pi times 5, which is the radius. Okay, now I solved out that equation ahead of time. So once we solve this equation, we find that the central angle is 45.0345. I just used the whole thing that my calculator gave me. And so now I'm going to substitute that for theta to the area formula. So the area would be 45.0345 over 360 times pi times 5 squared, since the radius of the circle is 5. Okay, when you go ahead and calculate that out, what you're going to do just using a calculator, to the nearest tenth you get 9.8, and so we have an area of this sector of 9.8. Okay, I know that was quick, but hopefully that was enough to get you started. I'm going to put your flashcard back up on the screen here so that you can copy those two formulas for arc length and area of a sector. So finish up the flashcard, and then don't forget to study for your quiz, and I will see you in class.